Hi, everybody. Thank you very much for the invitation. I was really pleased to get an invitation from a community interested about collapse because it's a topic totally understudied in academia, where I am working as a researcher, and of course in society. So I think this type of forums are very, very urgent. Okay, so I was asked to speak about the, let's say, the limits of green growth from a biophysical perspective. Before that, I would like to give an overview of which are the different transitions that are out there, no, in the society. My opinion is that there are different transition paradigms because there are different diagnoses of what is the problem. And there are different diagnoses because there are different perceptions of what are the risks we face. So that's the reason I would like to start a bit with this, and then I will go more deeper into green growth. So if you look at society in general, you can find three archetypes of the perceptions of the risks that we face at societal level due to sustainability issues. So there are people who think there are no major risks. So we could call them deniers, Trumpists, extreme right, no? So what is the strategy and transition paradigm? Nothing, just business as usual, make money, and so on. Then there is a big group of people, I will say in rich countries maybe is the majority, who think or recognize a degradation of the biophysical conditions. Of course, here I put a heat map. There are a lot of different levels. But okay, there is a degradation and we need to solve that. The main strategy to address this is mainly through mitigation, in the sense we have a problem, let's solve the problem. And green growth fits in this narrative, which is, as you know, the institutional solutions to our problems. And then we have, on the other extreme, we have people who think that collapse is well underway, which I believe is the organizers of this conference, mostly, that the dynamics which are already working are so strong that we cannot stop them, basically. So the strategy is adaptation. And I have put here in between something mixing that I will call people who think that, okay, we need to mitigate and adaptate. And I will locate these strategies around post-growth, degrowth, also acknowledging that there are a lot of also different versions of it. There are more people who think more that will be a more planned transition, so we have more control, or there are more people who think, okay, this will be like navigating problems, no? So the constants will be very strong. So I think this gives us a bit of panorama, and then I will focus on green growth. So it's not, I think everybody who is here is probably very aware that we are in a situation of overshoot. What does overshoot mean? Overshoot means in any biophysical system, or you can apply it also to a society, we depend on a resource base for our life. If we degrade this resource base, then our life will suffer, no? This is what we call carrying capacity. So we are in a situation of overshoot, which is, this is the carrying capacity in the dashed line, and we are over that. This is overshoot. This is studied by complex systems, system dynamics, and so on, and there are just two solutions, I mean, for this, because this is totally unsustainable. We are degrading the base life, so this needs to be brought back to the limit. First options, overshoot and oscillation, and then stabilization. And this is where green growth and post-growth degrowth are operating. So green growth is expecting, okay, we will stabilize always at a lower level because we have degraded, but quite high. And post-growth degrowth is trying to plan decrease this level of consumption to be well below this carrying capacity. There is a second option, which is overshoot and collapse. If the dynamics which have forced this situation of overshoot are too strong, you have a positive reinforcing loop that doesn't allow you to do any solution. And then you fall, okay? So this is, let's say, complex system science. There is no much discussion about this. Okay, what is green growth? I think everybody is familiar with the idea because it's, as I said, the institutional response to the problems. So everybody is familiar with this framework, but I want to really identify some key points. So the main point or the main objective of green growth is to achieve decoupling. Okay? What is this decoupling? In its history, the recent history, let's say since the Industrial Revolution, we have built economies, linear economies, which consume inputs from the nature and produce outputs. This is pollution and ecological damage. So we have a relationship which is, let's say, proportional. More production, more impacts, more inputs. So green growth is proposing to achieve absolute decoupling. So increase economic growth, but all the impacts reduce. Okay, this is, let's say, a wish. And then they have some ideas on how to do that, which, as I will try to show, have also quite a lot of problems. So main elements, of course, this is an institutional solution, is capitalistic, based on economic growth, based on efficiency improvements, new technologies for especially renewables, low carbon, electrification of everything that is possible. There is no problem with scarcities because the market is very smart with prices. You see scarcities, you substitute on time, don't worry, that will work. The policies and mechanisms they are thinking is, well, there is a broad umbrella term which is called circular economy. For me, circular economy and green growth are more or less synonyms because how are you going to dematerialize your economy? The only way, theoretically, will be that you are able to recycle everything in your technosphere, in your human society, and if you take something from nature, then you give it back. No? So for this reason, the circular economy is very, very central. I will talk more later about this. Okay. So before mentioning or going through the problems or failures that I see in this green growth approach, I would like to talk a bit more about the human social metabolism. Okay? So this is, I think, very important conceptualization to have in mind. When we talk about the human metabolism, it's basically because as a society, we work as a metabolism. We need inputs. We can be non-renewable or renewable. We process these inputs, energy, materials, water. We do things with them. We do production, consumption, transport, food. And then there are losses, and there are residues and ecological damage in form of emissions, in terms of habitat destruction. So everything that we take from the nature, the biosphere processes and ecosystem services, is degraded by our residues and activities, okay? So this is what here we have also implicitly the carrying capacity is degrading the carrying capacity. At the end, everything is a problem of scale, because if we are a small amount of people and we are damaging, the damage is small. But if we are a lot of people, so it's a problem in sustainability is always a problem about scale. So what happened with this degradation when we are not degrading the biosphere? Is not only that we are worsening the quality of our renewable resources, but we are directly impacting our social metabolism through mechanisms, for example, such as social impacts. You can think about health impacts. You can think about increased mortality due to climate change, diseases, etc. And this forces the system to increase what we call defensive expenditures. So this is because I am afraid that some problems will happen, then I have to extra invest into more infrastructure or capital to defend against floods, for example. You need to build bigger protections, whatever. So all this drains, of course, the, let's say, efficiency of the society, of the economic process. In terms of non-renewable materials and renewable energies, well, I will go directly to the limits. So this is at the end, you can study this from a thermodynamic perspective, because this is an open system, which, of course, to survive needs inputs from the exterior. So then the thermodynamical laws apply. I don't want to be here too much technical, but it's important that in physical science, when we say it is a law, it's not a theory or whatever, it's a law. It's something that applies under all conditions. It's not an ideology or an opinion. So some consequences inferred from these thermodynamic laws affect directly the technological limits of this, or accessibility of these resources. One critical point is the issue of quality. Okay, because I will give an example. The potential of renewables, no? There is a perception that it is enormous. It's true that there is a lot of wind blowing in all the planet, solar, while it is day, you have a lot of sun. But here the question is the quality, because you need to build systems based on materials, capital, or human labor to capture this energy. So at the end, are you taking more energy than what you invested to build it, for example? And I will talk later about an indicator which measures this, which is the ROI, energy return on energy investment. So the quality is not whatever energy, it's not whatever material. We need high quality materials to be able to process and that they are useful for us. Another deriving from the principles of thermodynamics is that there are 100% efficiency in the transformation of energy is impossible. I think this is common sense for most of us. It's impossible to reach 100% efficiency, but you need also to be aware that many times the theoretical limit is very far from 100. I will give also some examples later. But for example, for a solar PV, because there are different technologies, but for the typical solar PV, the maximum limit from a thermodynamical perspective is 30%, around 30% of efficiency from light to electricity. So we are far from 100 many times. Related with marginal returns, okay, at the beginning of the development of a technology, you do a lot of improvements. But then when you approach the limits, you have less options to improve, okay? It's a mature technology. Third element, very important, the close link between energy and materials. I think many times we see them differently. They are the same. Why? Because you need materials to extract energy. I mean, there is wind, but how do you capture it? You need to build something that has its infrastructure, it will have its lifetime, and so on, and then you will need to decommission. So without materials, there is no energy. But the opposite is also true, because without energy, there are no materials. You need to mine, you need to refine, you need to transport. So the two are totally interlinked. If at the end of my presentation, I hope I can show you some graphs about that. Okay, and then more specific about non-renewable resources. Of course, non-renewable resources, by definition, they are finite stocks, so they are subject to depletion. And, well, what I said about recycling rates, of course, applies only for metals, so there are also limitations to recycling rates. Yesterday, I mentioned you can only use recycled materials if you don't need too much high purity in your applications. But high technologies require high purity. For high purity, you need to mine. Even if you have stock to recycle, it will require so much energy because of this to recycle. It's impossible. Renewables have one specificity, which from the biophysical point of view, which creates problems in the transition, which is the variability. It's not news that at night there is no sun, no wind can change a lot. So this is an extra task for the system in a transition to renewables. And lastly, all this affect on the sustainable potentials of renewables. Okay, so now, this means 5 minutes? Sorry. Okay, so now, well, this is the general idea. Now I have given a lot of information. My idea now is to illustrate with some examples some of these ideas. If any of you is interested about other things I mentioned, we could talk in the Q&A. I have done a selection because of time. So, well, I would like to start with something that many times is overlooked, but I think is fundamental, is the depletion of non-renewable energy resources. So there is a lot of people, or in the academia also, the idea that, okay, if climate change is a problem, we need to reduce the consumption of fossil fuels. So the availability of fossil fuels is not a problem, because we need to reduce. Well, this is wrong. Why? Because 85% of the energy we use today in the world is based on fossil fuels. The transition, whatever transition there is, will be based on them and on materials. So if you want to do any modeling or any strategy about transition, you need to have this properly captured. This is not done, in my opinion. This, for example, is a figure I really love. This is extraction of oil in Norway, historic. I didn't find more updated data, but I mean, there are updated data, but they follow this. So you can imagine if a country such as Norway, so rich, access to the best technology, the welfare state depends on oil. If they are not able to extract more oil, it's just because there is no more. And this is an empirical demonstration of peak oil, and we could show figures for many countries. And now we live in an exceptional period because of the fracking revolution in USA. No one in peak oil foresee, I mean, that surge in oil extraction. USA is now producing an enormous amount of oil. I think they even started to export, which some years ago was unbelievable. But this is very constrained to the USA context. Okay, it's not easily at all extrapolable to other countries. And there I have a picture just showing that this phenomena of depletion affects many other, I mean, all of the other non-renewable resources. About renewables, as I said, the perception is that the potential is huge. So when you hear the word potential, there are a lot of adjectives that you can put to this potential. This perception of abundance comes from what it is called theoretical potential. But okay, for us it's not interesting, the theoretical potential, because I need to know how much I can harness and which gives me sufficient quality to sustain my level of life. This is the important question. So then you start applying constraints, geographical constraints. We are not going to go to deep ocean to take technology. Technical constraints, maybe there is some wind somewhere, but I don't know how to capture because floating systems, for example, have a lot of problems. Then you have economic conditions, and then you have sustainable restrictions. So it obviously doesn't make sense to cut primary forest to put solar panels. So there are also sustainable conditions. When you account for all these factors, the potential that you get is much lower than what it is usually state. And here it depends a lot on the country. It's not the same to power a country such as Holland or Belgium, which have a lot of people, a lot of energy consumption, very small country, or to power a country as Australia, no? And 25 million people for one. So here, it's really important to look case by case. Well, in my work, my main expertise is about simulation models. So in my group, research group, which by the way I didn't present, is called the Group of Energy, Economy and System Dynamics at the University of Valladolid. We do many things, it's a big group, but our biggest expertise is about building our own models. So the idea of building models is to try to simulate the future and to see what happens. You can simulate for doing an impact analysis to see, okay, what is happening, or to try to find some solutions. Okay, here I don't have time. There are different types of models, mental models. Well, this is, anybody is very interested, we can come back on this. So basically, we build systems which have represented human part, society, demography, economy, finance, and then we have biophysical part, energy, materials, climate, land, and water. This is from a model that we are developing. It's called William. And basically, what you do is to put some inputs on the model, you get some outputs. And now I'm going to give you an example about the materials for global transport electrification, which we use applying a predecessor model of William. So basically here we simulate different scenarios, but I want to highlight here a degrowth scenario, and this blue line is a, let's say, green growth scenario. The green line will be like a baseline. So you can see, depending on the strategy of the transition, the requirement of capacity of batteries is totally different. Here for a degrowth scenario is 10 times lower. So here it's important to have in mind, I don't know if everybody is aware that electric batteries are enormous, huge, 500 kilos on average. The Tesla models, which are luxury, is much more. So it's a lot of materials. All this is metals, mostly, and plastics. And here is very, very important to talk about sub-technologies also, because many times you hear, no, oh no, now there is a new technology of battery which solves all our problems. No, the typical problem with batteries and critical materials is because they use, the nice batteries, they use cobalt, nickel, and lithium, all critical materials. And then they say, no, no problem, we have another technology called LFP, which does not use cobalt and nickel, and everybody is, okay, it's very nice. But they are not saying that you are using other materials that have their own problems. So LFP does not have cobalt and nickel, but you have aluminum, phosphorus, iron, and copper. I will give later on another example. So basically in our simulations, what we see is that even if you try to increase a lot the recycling rates, at the end, if in a growing system, you always need more materials. So at the end, you need to mine. And in this result, what is also interesting, because we compare green growth and post-growth, is that, of course, post-growth requires much less materials, so less scarcities. But still, in the degrowth scenario, also, we will consume all the reserves of some of these critical materials. So this means that in the degrowth, post-growth community, we should also they should take account of these problems. Well, you know, European Union is now spreading in Europe sustainable mining, no? Well, because this circular, it's a bit counterintuitive, not circular economy, but then you have green mining. Well, now I would like to talk a bit about ROI, which is a metric in which I work a lot, which is a metric about how works the metabolic system of a society. So basically, if you look at it from an energy perspective, the society has an energy sector that is producing energy, and the objective of producing this energy is final consumption. No, we want to use it for transport, for diets, for house, for traveling, whatever, for production of goods and services. But we have to take into account that one part of this production of energy is used to power the energy system. It doesn't work alone. So when the ratio of this with relation to this is very high, when the ratio of this with relation to this is very high, the ROI is very good, and we say that we are in a situation of high ROI, which is very good for society. No? We are distracting low amount of resources. Look what happened. Imagine a situation where your energy quality is much lower, and you need to reinvest. You need much more energy to process materials, to extract, etc. So the amount of net energy arriving to society is much lower. Okay? This is our made-up graph just to show you. And so it's empirically, it has been shown that the ROI to sustain industrial societies needs to be minimum 5 and at least 10. And now I'm going to show you some results with William model about hydrogen. Why hydrogen? Yesterday also, well, the topic was raised. It's a very relevant topic. We cannot electrify everything. Electricity is not appropriate. It cannot power activities which require a lot of power, high distance, heavy things, high temperature. So that's the reason the European Union, among others, is promoting hydrogen. The idea is to feed an electrolyzer with electricity, renewable produce, transform this to hydrogen, and then produce synthetic fuels. What happens when we put this in William, which is a model which accounts for ROI? Almost no model computes ROI. Okay, this is biophysical economics, but it's not very popular, let's say, in science. So now we are in ROI, global ROI of around 10. This is a baseline. So, okay, if we don't do the transition, it will reduce because still renewables are entering. If we put a lot of renewables in the system, 80% of renewables in 2050, this is the green line. This is because we need to invest a lot of energy in the transition. If we put hydrogen with the hope to further reduce emissions, then look what happened with the ROI, because the hydrogen is introducing more losses. The hydrogen is introducing more inefficiency in the system. So you do reduce emissions, but at the cost of reducing your ROI a lot. The model is not so sophisticated. We are working on that. That is very complex. But I remember that I mentioned that any ROI before 5 is not compatible with industrial society. So that means that probably this wouldn't happen. There will be some feedback which will prevent that from happening. So this is, let's say, an impact analysis, biophysical impact analysis. I'm done. I will conclude. Okay, I have some slides about limits to technological improvements. I really like this part because I use news and so on. So, well, if you want later we can talk about technology in general and how we receive information from media. So some takeaways will be renewables are very far from being unlimited. I've shown some examples. The potential is in practice reduced by many factors, the practical potential. And another key idea is that we live in a paradox because we need to do the transition very fast to avoid impacts, but the faster we will do the transition, the impact will be boosted. So this is a problem. So I hope I have shown you that green growth faces underexplored shortcomings. The growth scenarios make things easier in theory, but they are still not totally defined. We can also talk more about that if you're interested. And then, well, I would like to finish my presentation with, well, the starting slide. We are here, and these are the two options that are on the table. Thank you very much.